5 miles beneath the surface of the Pacific Ocean, far beyond the reach of sunlight and human presence, a quiet but consequential race is unfolding, one that few people are paying attention to, yet one that may ultimately determine who controls the resources that will power the modern world in the decades ahead. Across vast stretches of the ocean floor lie fields of rounded metallic stones known as polymetallic nodules, unassuming in appearance yet containing within them a concentration of metals that have become essential to modern industry, including nickel, cobalt, copper, and manganese, all of which play a critical role in everything from electric vehicles to large-scale energy storage systems. For most of human history, these deposits remained completely inaccessible, hidden beneath crushing pressure and absolute darkness. But that reality is now beginning to change, and with it comes a question that is becoming increasingly difficult to ignore. Who will ultimately control the deep ocean and the resources it contains? China, more than almost any other nation, has already begun to answer that question through action rather than speculation. Its manned submersible, known as Fendoujia, has descended to the bottom of the Mariana Trench multiple times, reaching depths greater than 10,000 meters or more than 32,000 feet, placing it among a very small group of nations capable of operating at what is known as full ocean depth. And while these missions are often described as scientific exploration, they also represent something more subtle but far more significant: the steady accumulation of knowledge, capability, and strategic advantage in one of the least understood environments on Earth. At around 4,000 meters below the surface, roughly 13,000 feet down, the ocean floor transforms into what geologists describe as the abyssal plain, an immense and largely featureless landscape where time appears to move at an entirely different pace. Scattered across this plain are countless polymetallic nodules, some no larger than a potato, others closer in size to a human fist, each one formed over millions of years as dissolved metals slowly accumulate around a small fragment of organic material such as a shell or bone, gradually building layer upon layer into a dense and mineral-rich structure. Within each of these nodules lies a chemical composition that reflects the demands of modern technology, with typical samples containing measurable percentages of nickel, copper, cobalt, and manganese. Metals that are not only valuable, but increasingly critical as the world transitions toward electrification and renewable energy systems. Nickel plays a key role in extending battery life. Cobalt stabilizes battery chemistry under high temperatures and stress, while copper and manganese are essential components of power grids and transmission infrastructure, meaning that access to these materials directly translates into influence over entire industries. On land, the supply of these metals is often concentrated in a small number of regions. Many of those regions are politically unstable or geographically constrained. Examples include cobalt production in the Democratic Republic of Congo and nickel extraction in Indonesia and the Philippines. These conditions create vulnerabilities that can disrupt global supply chains. In contrast, the Clarion-Clipperton Zone, a vast stretch of seafloor between Mexico and Hawaii, is believed to contain more of these critical metals than all known land-based reserves combined. That reality has transformed it from a geological curiosity into a strategic prize of immense importance. China recognized this potential earlier than most. As far back as 2001, the China Ocean Mineral Resources Research and Development Association, COMRA, secured exploration rights in this region through an agreement with the International Seabed Authority. The area covered was roughly the size of Ireland. Those rights have been renewed repeatedly, most recently in 2023. Each renewal represents more than continued access. It provides time to map the seabed, collect samples, and build a detailed understanding of the terrain, knowledge that becomes increasingly valuable as the prospect of actual mining moves closer to reality. However, access alone is not enough. The true advantage lies in the ability to reach these depths, operate reliably, and return with usable data. It is here that China has invested heavily over the past decade. Early efforts included the submersible Jiaolong, which in 2012 reached depths of around 7,000 meters, demonstrating initial capability, but falling short of full ocean depth. That limitation led to the development of Fendoja, a far more advanced vessel designed specifically to withstand the immense pressures found at the deepest parts of the ocean. It has a titanium alloy hull capable of protecting its crew from forces more than 1,000 times greater than those at sea level. In 2020, Fendoja successfully descended to nearly 11 kilometers into the Mariana Trench, placing China among the very few nations capable of reaching such depths. But a single mission, however impressive, does not establish long-term capability. That requires repetition, consistency, and operational reliability. Between July and October 2025, Fendoja completed more than 40 dives beneath Arctic ice over a period of nearly 100 days, working alongside other submersibles in coordinated operations that involved precise positioning, data exchange, and synchronized observation, all under conditions that rank among the most challenging on Earth. This transition from isolated achievements to sustained operations marks a critical shift, one that separates experimental exploration from strategic capability. Each dive adds to a growing archive of seafloor maps, biological samples, and geological data, building a foundation of knowledge that no other nation currently possesses at the same scale. At the center of all this activity is the International Seabed Authority, ISA, an organization established under international law to regulate exploration and potential mining in waters beyond national jurisdiction. In theory, ISA acts as a neutral authority, ensuring that access to seabed resources is managed responsibly and fairly. But in practice, its role is complicated by the fact that the rules governing deep-sea mining remain incomplete. For years, companies and governments have operated under exploration licenses while waiting for a finalized mining code that would define environmental standards, operational limits, and legal frameworks. Yet that code has remained under negotiation, leaving a gap between technological capability and regulatory clarity. China, through multiple contracts and consistent participation, has positioned itself at the center of this process, accumulating both practical experience and influence over how the rules will eventually be written. In 2021, the situation shifted dramatically when the island nation of Nauru triggered a legal provision known as the 2-year rule. That effectively set a deadline for the International Seabed Authority to finalize its mining regulations, a deadline that expired in 2023 without resolution. This placed the International Seabed Authority in a difficult position, forced to consider mining applications even without a completed regulatory framework, increasing pressure on all parties involved. China, through its state-owned companies, has already proposed pilot mining operations that could begin as early as 2025. These would represent the first real attempt to collect polymetallic nodules at scale from the deep ocean floor. Such operations would rely on specialized collector vehicles, machines designed to move across the seabed, gathering nodules while disturbing the surrounding sediment, an action that has significant environmental implications. The abyssal plain, though seemingly barren, is in fact a delicate ecosystem where life exists in a state of near-perfect stability, and any disturbance can have long-lasting effects. When a collector vehicle moves across this environment, it creates a sediment plume that can spread over large distances, disrupting organisms that rely on clear water and stable conditions, and studies have shown that the impact of such disturbances can remain visible even decades later. Beyond metals, the deep ocean also contains other resources, including methane hydrates, sometimes referred to as fire ice, which represent a potential energy source, but also carry significant environmental risks due to the release of methane, a potent greenhouse gas. China has already conducted tests in these areas, demonstrating both the potential and the dangers involved. Taken together, these developments reveal a broader pattern. Over the past 2 decades, China has secured access, developed technology, and built operational capability in the deep ocean, positioning itself as a leading actor in a domain that is only now beginning to attract global attention. At the same time, other nations, including the United States, have begun to respond, sometimes through parallel approaches that exist outside the current international framework, raising questions about how this competition will ultimately be resolved. What is becoming increasingly clear is that the race for the deep ocean is not defined by a single breakthrough or discovery, but by a gradual accumulation of advantage, built through contracts, technology, and sustained presence. The resources at stake are not merely geological curiosities. They are the materials that will shape the future of energy, manufacturing, and global infrastructure. Machines capable of extracting these resources are already being developed and tested. The rules governing their use remain unfinished. What happens next will not be determined solely by who can reach the deepest point, but by who is prepared when the moment comes to turn access into control.